Today I will talk about a junction theory or and application to our problem, namely surfaces in P4. On Wednesday I will talk about linkage. But all the time with examples coming from classification of surfaces in P4. So let me, before I say anything more about the junction theory, say which examples I aim to look for today. So S is the surface of degree D, and pi the genus of a hyperplane section H. Then I will look today again at the two cases 5. So let's see, d pi equal to 5, 1 and 5, 2 that we briefly looked at last time, but also 6, 2, 6, 3 and 6, 4, degree 6, and all smooth surfaces of degree 6 in P4 will have genus 2, 3 or 4. In fact, we're going to show today that this is impossible. So I will actually show that this is impossible with a junction theory. So I'm just putting up this list of invariants for surfaces of examples that we'll get to. Two of them we already saw last time. So let me just to make sure that I claimed that this was an elliptic scroll. And I also claimed that the other one, 5, 2, is a rational surface. So we'll see that again today. So what is this junction theory about? Well, as I've said once before, if you look at the standard sequence on the surface, this standard sequence on the surface where H is a hyperplane section, if S really is a smooth surface, then this here, then H is a smooth curve, and this here is the canonical. By a junction, this is the canonical linear series or line bundle on the curve. So omega H is canonical so OH H plus K is canonical line bundle on H. And we know from curve theory that omega H is very ample, gives you the canonical embedding of the curve, unless H is hyperelliptic. So therefore, H plus K on the surface is a line bundle on the surface that, restricted to at least every smooth curve on the surface, is very ample. Except if you have some stupid curve on the surface which is hyperelliptic. This can very well happen, but if it doesn't happen, then you get something smooth. That the restriction of this to the hyperplane section is a very ample divisor. So I just want to, this is important as an idea. This is not the proof of anything, but this is where a junction theory comes into the picture. You see, you have, on the surface you have many curves. Now you have a linear system, or you have a line bundle on the surface whose restriction to all of these curves is very ample. Why isn't that also very ample upstairs? That's the question. Maybe it is, maybe it isn't, but still, there's a good chance that it is very ample upstairs also. It could fail, because it could fail at some of those guys, right? It could fail on the hyperelliptic curves. So if your surface has some hyperelliptic curve in the hyperplane as divisors, then you're out there, then there is something happening. But if there's not, then, yeah. So this is already the background for questions like the following. If you have a linear system of curves on a surface, can you have some curves in the linear system to be hyperelliptic and other ones not? Or put it differently, as a general classification, nothing with P4, but just in general, what are the linear systems of curves on the surface with hyperelliptic hyperplane section, that are hyperelliptic? So linear systems with hyperelliptic curves in them. What are they? Okay, they all come out of this setting here. This setting. And now I'm going to just write up the very beautiful result which solves all the questions I just asked. And this was assembled over some time, but it was proven finally in 1986 or something like that, published in that area. And it's called Theorem on a Junction for Surfaces. Before I write it up, let me also say this is a background also, this whole theory, if you replace S by a threefold and H by a surface, you may have a similar question. Of course, we don't know so much about the canonical series on systems on surfaces, but still, this junction theory has been used in classification also for higher dimensions. But there it was not effective enough. It was not effective enough. One of the reasons was that so you're going to lift this linear system to this guy here, and to be able to lift that you need so you're asking for sections here. This is not always possible. So therefore the Mori theory took over and solved the classification for threefolds and so on. But this adjunction theory is very close to the Mori theory. And so I think it's important to have this in mind, exactly this setup here, because we know this is chapter 4 something in Hodgson's book, you know, the canonical series on a curve is very ample unless it's hyperelliptic. Very nice and clean result. So here now S in Pn is a smooth surface and let me see, I want a few things, not so many actually. Well, I guess pi is the genus of H, and PG is the number of sections in the canonical bundle. So K is the canonical bundle on S, and this is the number of sections of this guy. Then I can formally set up the following. So I do it right this way. This is, if it exists, this is the map defined by the linear system H plus K, by this system here. Maybe there's nothing in it, but if it exists, you get a rational map. And this is sending your S into some space, and that is a space of dimension n minus 1, where this n is equal to pi minus 1 plus pg minus 1. So that's the dimension of this. So maybe I overlooked a little bit here. I'm sorry for going a little bit back and forth here. So this statement here says, of course, this is the case if pi is bigger than 1, right? When pi, well, it depends on what you mean by hyperelliptic. Maybe you would say a rational curve is also hyperelliptic, or an elliptic curve is hyperelliptic. But anyway, this is, and you see if you have pi is equal to 0 or 1 here, you often get something very small. But let's move on, because I think the result says most. Then it says the following: if this is the setup, then this here is a morphism, in fact is a birational morphism onto a smooth surface flowing down only -1 lines. -1 lines, what's that? These are lines on the surface. Lines on the surface with self-intersection -1. -1 lines. Okay? Well, there must be some exceptions. And that is certainly true. Unless the following happens. Well, the first case is that S is a plane. Is a plane, a Veronese surface, or a scroll. This is the case where H plus K is empty. Two. S is a Del Pezzo surface. Or a conic bundle. So this is the case where h plus k squared is equal to 0. And then 3. X is rational. H is either 6, 2 to the 7, 6, 2 to the 7, and 1, and 9, 3 to the 8. Or finally, or X is elliptic, P1 bundle, H is 3B, where B squared is equal to 1. Well, I'm sorry for writing small there, but this is the end. That's the whole thing. So let me explain a little bit what it says here. So first of all, the big class is the first one, where it says everything is fine. In fact, if you have no -1 lines on S, no lines on S that have self-intersection -1, then this is in most cases just an embedding. This is an embedding, just like I was hoping for over here. So the exceptions are, first of all, those cases where H plus K have no curves in them at all. No global sections for H, so no global sections there. This would be, so no global sections there, I'm sorry. So that's typically in cases, well, the ones that are described here are precisely when the surface is rational, is P2, then H plus K is negative. If it's P2 with, if it's a Veronese surface, then it's still negative. And the third case is where the surface is a scroll. The surface is a scroll. Just think about if the surface is a scroll, then the hyperplane section here is, so it means, an F, a fiber, a ruling in the scroll. Then the hyperplane section will intersect each fiber in one point. That's when it's a scroll. The canonical divisor on a scroll will intersect each fiber in -2. And that's actually by a junction. The fiber is a P1. Is a P1. So F times F plus K should be -2. And F squared is 0, so F times K should be -2. And so here you see immediately that H plus K restricted to F is negative. So it couldn't have any sections. So you have to be in this first case here. Also, another way of saying it is you have all these rational curves, all these rational lines. So what is the restriction to those? It's negative. So that's this case. The next case here is the Del Pezzo and the conic bundle case. They are both characterized by the fact that H plus K, well, you will have some sections, but the square here is 0. If you take two sections, they have no common points. No common zeros. And in fact, if you think about that for this map, so you might have, I'm saying you might have many sections here, but the map is no longer, have no chance of being an embedding. It's actually a map onto a curve. So this case, when H plus K squared is 0, you get actually a map of S onto a curve. Or in fact, to a point in a particular case where H and K are just opposite each other, when H plus K is a trivial bundle. So let me spell that out also. Actually, so I hear the Del Pezzo. The Del Pezzo surfaces are exactly the surface where H is equal to minus K. Which means that H plus K is trivial. It's a structure sheaf, right? And that has certainly a section, it's a constant section, so you get the map to a point. That's all fine. So that's the Del Pezzo case. What about the conic bundle case? Why conic bundle? Or where could conic come into the picture? Well, it is actually the case, and now I can use this thing here, a conic bundle, same as so it's birational to a ruled surface. So conic bundle means that you have a map of S onto a curve where the fibers are conics. And so the fiber here is, well, S is the conic bundle and F is the fiber. What we're saying that is H times F now should be 2 for conic. Well, still by the adjunction then, by adjunction here you get exactly the same as before, that Fk is equal to minus 2 here. So now you see that H plus K applied to F is just 0. So it's just 0. So you have this linear system on that surface, or the line model H plus K on that surface, and on each fiber it's trivial. So it contracts all the fibers onto the curve. Okay? So that's this conic bundle story. So of course that's exactly this what's going on here. And yeah, okay. Let me see. So that's that. And then we have some exceptions here. And here I will just say what the notation is. I introduced that briefly before, but the exceptions here means So what does it mean? For a rational surface, it means that S is the blow-up of P2, and well, I have a line here which is pulled back to a line L, and then I have points that are blown up to E1 up to ER, and then my age is going to be some AL minus the sum BI EI upstairs, and the notation for that is just A and then B1 up to BR. So that's what I mean by this here. Well, I put the 7 here, it just means 7 twos. Sextics, so I think of this as plane sextic curves with 7 double points. With 7 double points. So these exceptions show up. They're not going to play any important role for us. They are interesting in themselves to know what's happening in those cases. Well, I could say that other thing is I will say in those cases is that precisely these cases, then H plus K, this adjunction mapping is going to be 2 to 1 onto a surface. 2 to 1 onto a surface. So these are exactly the cases where you have hyperelliptic hyperplane sections. That exceptional sets of such things. Okay. So let's see now if we can. Well, one more thing I want to say before I'm applying this to examples. I didn't say anything explicitly about this blowing down of -1 lines. What is that? Why is that there? Well, so now I erase this here. So now if you assume, if you have exceptional curves of self-intersection -1, it means that you can always blow them down. So if you have E on S with self-intersection -1, so EI, so these are exceptional. So these can be blown down to S0 with S0 still smooth. If you have any curve of self-intersection -1 upstairs, well, I should say EI should also be rational. Must also be rational. Okay. Then you can blow it down. Well, if that is the case, if you look at the adjunction on EI, we have EI plus KS times EI. Since EI is a rational curve, this here is the canonical on the curve EI. So therefore this is -2. Okay. So I get EI squared plus EI times KS equal to -2. And since this is -1, this is also -1. EIK is also -1. Right? So now if I have H on S and E on S. If H times E is, well, it is some number. This is some number. Well, if this is 1, then H plus K times E is equal to 0. Yeah? In fact, if this here is equal to A, then you get here A minus 1. Always get it reduced by 1. See that? So since H plus K times this E is 0, it couldn't possibly embed this curve. It would have to contract this curve. So it means that if all of these are minus 1 lines, then the H plus K would map, well, the map defined by H plus K would factor through this map here, through the blowing down of those. So that's the reason for these minus 1 lines here. Okay. So that's a question now. Can we use this? Well, any questions so far? This is really this is the big theory in a way. I mean, this is a junction theory. So it's a collection of many results put together. And the big thing, the major issue in a way is that is the idea that I started with, and then the fact that this can actually be sorted out this way is very nice. And now it's going to be very effective for us, for our classification. So let's see. So let's start with these two guys here. So degree 5 and 1. And I need to first also write up the double point formula that I started with altogether, because I'm going to use it. D squared minus 10d minus 5hk minus 2k squared plus 12 chi is equal to 0. So this is the numerical restriction that we have. And 5, 1, this means that d is 5 and pi is 1, so hk, so d plus hk is equal to 0, so hk is equal to minus 5. Okay? And now I can look at this double point formula, what it gives me. So I get 25 minus 50 minus 5 times minus 5 is plus 25 again. So this all cancels out. Minus 2k squared plus 12 chi equal to 0. So I get k squared is equal to 6 chi. K squared is equal to 6 chi. I think I will need one more thing, so I should introduce we've looked at this sequence a few times. The ideal sequence, this is the ideal of S twisted by 1, and then ideal of H twisted by 1. I look at this sequence and I look at the numbers inside here. Well, I get on H0 I get nothing there. On I get nothing there, and here this is a hyperplane section. This is genus 1, degree 5. This is 5 sections by Riemann-Roch on a curve. 5 sections. There's an elliptic curve, and the curve has the divisor has degree 5. So Riemann-Roch says that this is 5. So I'm sorry, these two are 0, but what I wanted to say is that when you have 5 sections here, but the curve is a hyperplane section of our surface, so the curve lies in P3 and not in P4, so I therefore have this 1 for H1. So the first line is just saying that that surface lies in P4 and not in the P3, etc. But here I get a 1 because the elliptic curve, the hyperplane section, spans only P3, but it has degree 5, and the number of sections of a divisor of degree 5 on the elliptic curve is 5. So if you use them all, you get into P4. That's why this is 5. So by Severus Theorem now, we have nothing there. The surface is linearly normal in P4. That's this thing here. That's Severus. So we have 0 there. Now, and but the 1 there means that I have at least a 1 here. So, and what is this? What is this? Well, let me show you just in one case here. In this other sequence, you have also the ideal sheaf, and then you see that the H2 down here is the same as H1 of this thing here. Okay. So here we get, so what we get from this here is that H1 of O of S is at least 1. Okay. If we now look at H2 O of S, this is equal to H0 of K, but HK is minus 5. Minus 5, so this couldn't have any sections. So this is 0, because HK is negative. There's no way you could have a section that meets this hyperplane section in negative number of. So there's nothing there. I get a 1 there, and so therefore all of this means that the chi here is, well, which is h0 of O minus h1 of O plus h2 of O is less than or equal to, well, you have 1 there and at least 1 there, so it's less than or equal to 0. So this means this here is less than or equal to 0. So let's see, look at this very carefully. So I use these sequences here to say that we have irregularity. And that was really the key. And the next here is that hk is negative, so I have no sections for h2. And therefore the chi, which is the alternating sum here, is negative. Or not positive. 0 or negative. 0 or negative. So now we can go a little bit further. We say, we look at the classification of all surfaces. If chi is negative, so maybe I erase this. If chi is negative, then k squared is less than 8 chi. Less than or equal to 8 chi. So this is for ruled, so these are ruled surfaces. P1 bundles over curves. And the self-intersection of the canonical, if it's minimal, it's just 8 chi. If it's non-minimal, it's even less than that. So this is a general, very general classification result. So, but this means that k squared is 6 chi is equal to 0. It's actually equal to 0 there. Okay? And then now I'm almost through, because h plus k squared, if I just look at h plus k squared, I forget about all the rest here. Look at h plus k squared, I get 5 minus 2 times 5 plus 0, I get minus 5. H plus k squared is h squared, which is the degree. hk is minus 5. And k squared, I just showed this was 0. So I get minus 5. H plus k squared is minus 5. And if I go to the junction theory, this seems, if you go, I have something on the top and something in the bottom, and the only thing that is fitting here is that I have no sections. If I have a negative self-intersection for h plus k, there couldn't be any sections. And it's not P2 or a Veronese, so it must be a scroll. It must be a scroll. Okay? So there are many things going into this, but this table, you know, many of these things can be analyzed per se, you know, for themselves, you know, without going to the general junction theory. But this is really powerful and very nice to have in the background, you know, just to check. So here I'm just pointing out h plus k squared negative. Well, it has to be a scroll. Has to be a scroll. Okay? So that's actually this case. Let's look at that. Let's look at the next case, 5.2. And remember, as I erase now, remember that we saw in the case 5.2 that this was arithmetically Comic-Colli. And it was given by a matrix of this kind. We've developed this notation in this class. So when I have a matrix with numbers, it's arithmetically Comic-Colli. If it's just a line of numbers, then it's a linear system. Okay? So this is the Comic-Colli case. So this is, it says that the surface is, the ideal of the surface is defined by the maximal minors of a matrix with 4 linear terms and 2 quadratic terms. And why is it rational? Well, if I look at this matrix, and if I take these two, if I look at the plane defined by these two guys, so these two linear forms, then in that plane the surface intersects along the conic defined by this guy. And I have a whole family, a P1 of such things. So I had a P1 family of planes. Each of those planes intersect the surface in a conic. So this means I have in 2 different ways rational curves. So this is a rational surface. So let's get the linear system of this rational surface. So we should compute all the numbers. So the degree, as I said, is 5. H times k. Well, if the genus is 2, then h squared plus hk should be 2. So this is minus 3. And chi, since it's rational, is 1. So now if I'm using star to get the last invariant. So 25 minus 50 minus now, and this 5 times minus 3 is plus 15 minus 2k squared plus 12 chi. 12 times 1 is 0. So here I get this is 40 minus 50 is minus 10 plus 12 is plus 2. So I get k squared is equal to 1. Okay? K squared is equal to 1. So now I go with the hope of the previous example. I go straight for the h plus k squared. What is it? What is it? What is it possibly? H plus k squared is equal to 0, as you say, right? This is 0. You computed it, 0. So we must be in some case here which is, somewhere, right? In fact, these scroll cases, as I said here, that's not, I said here, because here I didn't say other sections. I'm just looking at this numerically. But I'm with chi equal to 1. I'm in chi equal to 1. I'm on a rational surface. On the rational surface. So then h plus k squared means really that you have a map. So you must be in this case here. You must be in this case here, meaning there must be a conic bundle. And somehow we also already saw this. I already explained this. I looked at the planes defined by these forms here. They intersect the surface along the intersection with the quadric. So that's a conic section. So you really have the conic sections here spelled out. Okay. But we should try a little bit more here to see what's happening. So let's just put up the sequence. See a little bit more of this, the mapping here. So since it's rational, I have nothing here and I have nothing there. I have nothing in those two places. So this gives me, in the rational case, a very strong incentive to look at this comparison here. Because I have the same number of sections, both here and here. See? This is 0 and 0. So, and here I know right away this is the canonical on a hyperplane section, and the hyperplane section is this curve of degree of genus 2. This is genus 2. A genus 2 curve has exactly 2 sections, right? It has 2 sections here. So therefore this is also 2 sections. So I have my surface S and it's mapped to P1 by H plus K. And the fibers, so the fibers are all conic sections. Okay. So what more is there to say? Well, there's a little bit more to say, because the way I've written it here, it looks like S is a nice P1 bundle over P1. Each of these are isomorphic to P1. Looks like it's a P1 bundle over P1. But that's not the case. It's only a conic bundle, so there might be some fibers here that are singular. There might be some fibers that are singular. Okay? So what would such a fiber look like? Well, so the whole fiber has square 0. If F has 2 components, F1 and F2, then I'm looking at something of the following kind, F plus F1 plus F2, square 0. And I know that the 2 fibers meet in a point, so I have 2 in the middle. So I have something of this kind here. Right? So what could it be, you know? Well, this is a rational surface, but these fibers certainly do not move. Like, if they move, they should move in this direction here. They don't move. So their self-intersection is negative. Self-intersection is negative. So both of them has to be -1. So these are two -1 curves. And it makes perfect sense if you think of S where this is minimal. If this is a minimal surface, when I've blown down all the -1 curves I find, then this is going to be a P1 bundle over a P1. So going the other way, I have blown up some P1s in points. And those fibers, the fibers of those points, will exactly split in two pieces. That the strict transform has self-intersection -1, and then the exceptional has self-intersection -1. So that's exactly what explains this behavior here. And in this picture we have exactly the same as we had for the general one, that the H plus K will certainly collapse the -1 lines. These are -1 lines. Both this one and that one are -1 lines. They will be collapsed. But they will be collapsed in this case together with all these other fibers. So we have collapsing all over the place. But including these. I'm just explaining this because it's the natural general phenomena also happens here. And now we connect. So next thing is, how many such things are there? How many for our surface? How many guys like that are there? How many points did I blow up? Well, this I can compute from this number. Because my surface is rational. So if it's the minimal surface, this one here, KS0 squared, is 8. When you have a P1 bundle, the self-intersection of the canonical is 8. If it's P2, it's actually 9. Right? And it drops by 1 every time you blow up a point. So the difference between 8 and 1, 7. So we must have blown up 7 points. So there's 7 altogether. 7 altogether. Okay. So then I could do this in different ways. I could say, if this here is P1 cross P1, then my system H is going to be of this type here. Let me see. It shouldn't be exactly. It should be A times this one, and then this one here. Does that make sense? So this is 1, 1. This is a linear system of type. Well, yeah, no, I don't think I want to. So I should rather put it this way. It's of type AB and then 1 to the 7. So if you think about the P1 cross P1, you have linear systems of type AB on this, and they pull them back up here. Then I get this thing, and then I've blown up extra 7 points. The difference between this number and this one. So these points here. Okay. And now, since the genus pi is equal to 2, you get immediately that A is equal to 3 and B is equal to 2. That's the only possibility. Because the genus here, this is equal to A minus 1 times B minus 1. And the two numbers must be positive. So that's a linear system there. That's not That's not the one I wrote up when I first presented this. You see, when you start blowing up P1, if you blow it up in one point, then you actually have a map also down to P2. So as soon as you've blown up one point, you might as well think of this as blowing up P2 in a number of points. Okay? So let's see how that works for us. So if we want to do the same thing, find a linear system on P2 blown up now in 8 points altogether. Let's see what's happening. So if S is equal to P2 blown up, then the hyperplane section is of the following kind: AL, and then it's B1 up to B8. Right? Furthermore, I know that most of these are ones, because I know I've blown down, these are lines. B2 equal to B3 equal to B8 is equal to 1. So I actually have A and then B1 and then 1 to the 7 for H. So I'm sorry for being maybe fast here, but let me repeat. If I think of my surface S that's blown up P2, I know, since k squared is equal to 1, that I've blown up 8 points from k squared equal to 9 down to 1. I've blown up 8 points. Also, I know that I have 7 special fibers here, so I have 7 minus 1 lines. Actually, I have 14, but I cannot use 14 because I'm blowing up 1 and the other one survives somehow in the comparison with this thing here. So it's actually 1 to 7. So I take the last 7 here to be minus 1, be lines. So then the system is curves of degree A with 1 point of multiplicity B, and then 7 simple points. And now H plus K, so, well, K, what is that? K is minus 3 and 1 to the 8. Right? Is minus 3 and 1 to the 8. So H plus K is equal to A minus 3 and then B1 minus 1, and the rest are 0. A minus 3 and B1 minus 1, and the rest is equal to 0. That's the linear system H plus K on S. So it's like a curves of degree A minus 3 that passes through the first point with multiplicity B1 minus 1. So H plus K. Yeah. So maybe I spell it out with this thing here. A minus 3, L minus B1 minus 1, E1. I know that H naught of this thing is equal to 2. That's what we had here. we have that this is a map to P1. We also know that h plus k squared is 0. So I see that a minus 3 squared minus b minus 1 squared is equal to 0. And the number of sections is this here. So a minus 3 is equal to b1 minus 1. And they should both be, well, we're looking at curves passing through a point with the same multiplicity as the degree. So this here is actually equal to, so these must be equal to 1. You see that? So just this computation, I get a minus 3 and b1 minus 1, and the self-intersection is 0, means that these two are the same numbers. So just think about this geometrically. You have you have curves of degree a passing through a point with multiplicity a. And those curves are just multiple of lines, right? So a L minus a times E1. So that's not the same as this one. Maybe it's alpha. Alpha and alpha. And the number of sections for this here, well, if I take alpha equal to 1, I get just the lines passing through, that's just 2. If I take alpha equal to 2, I take double lines passing through. You have actually 3 sections. So this is actually always equal to alpha plus 1. It's always equal to alpha plus 1. You can use Riemann-Roch or anything, to get that. If this is equal to 2, then alpha is equal to 1. So all of this computation says that this h, in that case, is equal to 4, and then 2, and 1 to the 7. I go back. And it explains everything. So, yeah, I went to the details of this just to get the numbers. So now I'll go also to the these cases here briefly. Just want to hear any questions on this. So there are many details in this, of course, and some of them has to do with geometry, and some of them has to do with just numbers, right? But exactly this interplay that I want to interpret the numbers all as we go along, just to see that it makes sense. Often, of course, these things can be presented more quickly, but the ideas here they come into play sooner or later. So let's see. Let's look at this case here first. Let's look at this case here to see that this is impossible. So now we basically did everything with degree 5, although we will come back once more also Wednesday to the elliptic scroll. So 6.2. Well, first of all, I noticed that if I have a genus 2 curve of degree 6, it's linearly normal in P4. So if it is a hyperplane section of a smooth surface in P4, it's not linearly normal. So I have the same phenomenon as I had with the elliptic scroll. And to spell it out, I have in this case here immediately, well, on the zeroth I have just zeros all the way, but on the one case here I have a 1 over there. Since I had a 0 from Severi, I get at least a 1 there. I get at least 1. So it means that H1 of K, or OS, is at least 1. So this is the first thing to keep in mind. The next thing that we will get from that, if I look at the invariance, HK in this case, since H squared is so this is 2 pi minus 2 minus H squared by the adjunction. 2 pi minus 2, that's 2 minus 6, this is minus 4. HK is minus 4. So this means that H2 of OOS is 0. And together with the previous one, this means that the chi is less than or equal to 0. Altogether. Okay? Now I use the star, and I get 36 minus 60 minus 5 times minus 4, that's plus 20, and then minus 2k squared plus 12 chi equal to 0. So here I would get 56 minus 60 is minus 4. So I get 2k squared is equal to 12 chi minus 4. So k squared is equal to 6 chi minus 2. Okay? Whatever that means. But I have chi less than or equal to 0, and this can work out. I mean, if you now compute by adjunction that we used today, because this here means that k squared is less than or equal to minus 2, right? Since chi is less than or equal to 0, I get less than or equal to minus 2 there. So now h plus k squared is 6 minus 8 minus, well, it's less than or equal to this thing here, which is negative. So this means that S is a scroll. And by scroll I really mean minimal scroll now. It's not a conic bundle, it's minimal. Which means that k squared is equal to 8 chi. Yeah. So this, well, if chi is equal to 0, I get a contradiction here. And if chi is equal to minus 1, which is possible, then you get the same number here. So this means that chi is equal to minus 1. Six chi minus 2 is equal to 8 chi when chi is equal to minus 1. And so this makes perfect sense that S, well, is a scroll over a curve, and where the genus of the curve is 2. Genus 2 curve. Then the chi is minus 1. And we started out here with something, it's degree 6 and genus 2. If I have a scroll, then the genus of the scroll and the genus of a hyperplane section is the same. I just intersect each fiber in one point. So this makes perfect sense. Okay, so this is the situation. We have this scroll, and we have as a possibility by the junction theory. Still, is it possible to find this as an embedding? This is just numerics so far. Just numerics so far. All the numbers are fine. The double point formula is fine. And this junction theory was fine. Could it still work out? So this is where you have to dig a little bit deeper. Of course, you can look at all kinds of P2 or P1 bundles and see what are the possible sections and so on. But you can also go straight for the geometry. Here is our surface. It's a scroll in P4, but each fiber is a line. Okay? Now, the hyperplane section cuts as a curve like that, and every section of this is a smooth genus G curve, genus 2 curve. Every section is a smooth genus 2 curve. All is fine so far. Now I'm going to look for some special hyperplane sections. Some special hyperplane sections. Which ones? Well, I pick out 2 of these lines. I pick out 2 of these lines. This is my first and this is the second line. I pick out 2 lines. Well, 2 lines in P4, they couldn't possibly span more than a P3. Couldn't possibly span more than a hyperplane section. Right? See, now I'm back to the very beginning. I'm in a space and I have some lines in this space. And if I take 2 of those lines, they span just a hyperplane. So I take that hyperplane and intersect that hyperplane with the surface. I get the first line and the second line and something more, something else. I call that something else C. When I look at the map, these 2 lines are mapped to just 2 points. But every hyperplane section is going to cut every single line. Right? So this curve here is mapped, well, maybe I should call it CH here or something, CH. It's mapped down to C, to that curve. And CH is actually isomorphic to C. If the surface is smooth, then this is isomorphic to C. Because it's 1-to-1, I mean, nothing's wrong. What is the degree of this thing? Degree of CH is equal to, well, the degree of the whole thing is 6, has degree 6. This is degree 1 and this is degree 1. So this is degree 4. I get the genus 2 curve of degree 4. The genus 2 curve of degree 4. So the question is whether there are smooth genus 2 curves of degree 4. And the answer is no. No way. That curve is a plane curve with one node. It has acquired one node. What this is actually telling us is that this surface may very well exist, but not as a smooth surface. In the sense that there might be a scroll in P4 of lines which is birational to a smooth scroll over a genus 2 curve. But for every such pair of lines, you'll get a section which has one node. Now the formula here says that you have 0 nodes, right? Well, what's the contradiction? The only contradiction is that these numbers here, they don't really count if you have infinitely many nodes. So if you have this guy here is going to have some nodes, infinitely many nodes along a line or something like that. So for every choice of 2 lines, you get a singular thing, singular node section. But I don't worry really whether this exists or not. It could possibly exist with such a thing. I just know it could not possibly exist at a smooth surface. And despite all of these nice things here and the double point formula, I need to go down, break it down to geometry, to get to the end of it. But that's the argument. That doesn't work. Okay. But this is, so that's this case. So let me, although I'm going a bit almost over time, but I will actually briefly say something about this case also when it's rational. So first of all, we know that we start with a hyperplane section. The hyperplane section of this is a curve of degree 6 on genus 3 in P3. And such a curve is either hyperelliptic or non-hyperelliptic. Well, that's like T, right? Either you like it or you don't. Except that here I'm saying something about every single smooth surface, smooth curve in the system. And as a hyperplane section, this here is ACM, and this here is 2,4, type 2,4 on the quadric. These are the 2 cases there. So I'll get back a little bit to this description. Well, ACM means that we know already from the description of the hyperplane section what the surface should look like. So this actually is the case where I have a Hilbert-Burt matrix like this. The 3x4 matrix are linear forms, and the 3x3 minors generate the ideal. But I do have time, a minute, just to get the linear system also. I get to get the linear system actually, in this case. Because h squared is 6, hk is, since it's genus 3, well, it's 2 pi minus 2 minus 6, So this is minus 2. And chi is equal to 1. This means that the double point formula gives me 36 minus 60 minus plus 10 minus 2k squared plus 12 is 0. So what do I get for k squared? 46 minus 60 is minus 14 plus 12 is minus 2. So k squared is equal to minus 1. K squared is equal to minus 1. And now if I use h plus k, look at the square, what do I get? I get 6 minus 4 minus 1 is equal to 1. So this map is mapping our surface after blowing down the minus 1 lines, is mapping it to a surface of degree 1. There's only one surface of degree 1, that's the plane. This is a rational surface, so this is perfectly fine. This is an embedding, right? So this means that h plus k is equal to just L, the linear system L. And therefore h is equal to, since k is equal to minus 3L plus the sum EI, plus for all the exceptional ones, then what I get is 4L here minus the sum EI. And since it's minus 1 here, I get 1 to 10. This is quartics through 10 points. That's a linear system. So in my brief notation, it's 4 and 1 to the 10. Now you actually dig it out from the from this thing here. So I will not go to 6,4. That's just a complete intersection. It doesn't matter so much. But let me give you something to practice on. A problem. Find linear systems for smooth rational surfaces, of degree d equal to 8 and pi equal to 5 and 6. Essentially using a junction. You could also try, of course, d equal to 7 and pi equal to 4. By just looking at the junction a couple of times. Okay, so I should definitely stop now. Thank you.